All right, welcome back, everybody. And we are going to start chapter 8. And stick with me. The lessons are going to get a little harder from here on out, but it's nothing that we can't do. We're still going to be looking at our normal distribution curves. We're just going to be calculating a few new things. And at the end of all of this, I'm going to show you how to use a calculator, which will save us a lot of time. So don't get too bogged down with the symbols and all of that. I'll tell you about it all in just a moment. All right, so for this lesson today, we're going to be looking at averages again. We're going to look at averages of a sample. So for example, we have M&Ms in a bag. If we want to find the average number of M&Ms in the bag, we can go and get a bunch of bags of M&Ms, count them up, and then take all those numbers and then average them. But we're going to go a little bit deeper in this. We're going to try to find the probability after we do all that our average would be between two numbers. And that's called a confidence interval. So we're going to say like 90 or 95% of the time we know the average of the bag, or we know the bag will contain between this number and this number. And that's going to help us later on in this course. So once again, we're going to go back to our normal distribution curve, and we're going to be looking at sample averages, sample means. Our normal distribution curve, once again, has the average right down the middle. And we're going to calculate these values on the sides as we've done before. So we use sample data to make generalizations about an unknown population. Sample data helps us to make an estimate of the population parameter, so about the population we're looking at. And we realize the point estimate, we'll talk about that in a moment, is most likely not the exact value of the population parameter, but it's close to it. So after calculating point estimates, that would be like the average of each M&N bag, we create interval estimates called confidence intervals. So this is called inferential statistics because we're going to be using our inferences to draw judgments about a larger population. So we're using a sample to draw something about a larger population. So first of all, we talked about something here. It was called a point estimate. And a point estimate is just when you calculate an average. So if you're trying to determine the percentage of times you make a basket when shooting a basketball, you count the number of shots you make and divide that by the number of shots you attempted. And in this case, you'd obtain a proportion of your shots made. Or if we're trying to find the average rent of a 2-bedroom apartment in your town, you look at a bunch of ads, you write down how much the rent is, and you take the average. That's called a point estimate of the true mean. It's one piece of data. Confidence interval is another type of estimate, but it's not just one number. It's going to be a range of numbers. And inside of that range, we're going to have a percent of our data that falls. And to calculate this, we take the point estimate, which is generally going to be our average. We're going to subtract the margin of error. We'll take the point estimate, our average again, and we'll add that same margin of error, and that will give us a range of values. The margin of error, we've seen that in polling predictions as well. It depends on the confidence level or the percentage of confidence in the standard error of the mean. So that depends on that standard deviation. Okay. So suppose we don't know the population mean and the mean number of songs a consumer downloads a month from iTunes, but we do know the population standard deviation. The standard deviation is 1. We take a sample size of 100 people. We find that their average number of songs they download per month on iTunes is 2. So by using the central limit theorem, we could go ahead and make a normal distribution curve that looks like this one up here. And using what we worked on last time, this is a sample standard deviation. So we use the standard deviation of 1 divided by the square root of the number of pieces of data, 100, and we get 0.1 for our sample standard deviation. And then we could use that 0.1 for our sample standard deviation. Suppose they wanted to look at the data that was within 95% of the average, or sorry, the middle 95%. So not within 95% of the average, but just the middle 95%. And that's within 2 standard deviations of the mean. We talked about that a little bit in chapter 1. And so for that, what we're going to do is take two standard deviations, and we're going to subtract those from the mean and add them to the mean. We get a range of numbers, 1.8 to 2.2. So our left side would be 1.8, our right side would be 2.2, and 95% of the data would fall within that region. So we're 95% sure that the population average number of songs downloaded from iTunes per month is between 1.8 and 2.2. So if we took another group of 100 people, 95% of the time, the average will fall in that range. Okay. So to calculate the confidence interval for a single unknown population mean, the population standard deviation is known. We need the average, an estimate for the average, and we need the margin of error. And so our point estimate, that's going to be our average. So that's going to be right down the middle. And our population average and our our population average and our sample average are going to be the same number. And what we're going to do is calculate this margin of error, also known as the error bound measurement. So the error bound for a population mean, abbreviated EBM. So what we're going to do is take the point estimate and subtract this error bound, and we'll take the point estimate and add the error bound. So if we look up here, the average is right down the middle. We're going to add this error bound and subtract it, and that gives us the interval on the left and right side. Okay. So to calculate this, confidence level is often considered the probability that the calculated confidence interval estimate will contain the true population parameter. The confidence level is the percent of confidence intervals that contain the true population, and so on. We use alpha for our population probability, and it's related to the confidence level. So alpha is going to be a percent, and CL will stand for the confidence level. So this is just a fancy way of saying the area in the blue, the confidence level region, plus the alpha region, the two tails, the white part, that adds up to 1. And we already knew that. The area underneath this curve adds up to 1. Take note, this alpha region, they divide it by 2 because that's left on both sides. So if this confidence level was, let's say like 90%, that means there'd be 10% left for the left and the right side. So that's why they divide it by 2, because 10% divided by 2, we'd get 5% on each side. So that's all that this is saying, that this adds up to 1. This middle part plus the two tails adds up to 1. So if this middle part was 80%, the two tails would be what, 10%? Because 20 divided by 2, 10. All right. So suppose we collect data from a sample. We know the sample mean, but we don't know the mean for the entire population. The sample mean is 7. The error bound for the mean is 2.5. The confidence interval, so if they give us the average, they give us the error bound, we can go back to our main formula here. We take this average, the point estimate is also known as the average. What we're going to do is add and then subtract that error bound. And so we subtract this 2.5 and add the 2.5 to the average, and it gives us our range of numbers. So between 4.5 and 9.5, this one we would have 95% of our data. We'll talk more about those percentages in just a moment. That's just a general one. Okay. So it's going to get a little more complicated though, because we need to find what's called the z-score to calculate this error bound measurement or error bound mean. Okay, so think back to our z-scores and our normal distributions with a mean of 0 and a standard deviation of 1. So let's look at this example. So we're going to look at a problem with the confidence level of 0.95. So the blue region will be 0.95, which tells us we have 0.05 left over. So that's our alpha. So to find each tail, we take the 0.05 divided by 2. We get 0.025. So that means we need to find the z-score when our tails have 0.025 or when the middle part has 0.95. It doesn't really matter. So what we can do is go into our calculator. I'm going to go into my inverse normal distribution calculator. We were looking for a middle region of 0.95. And I'm going to keep this mean at 0 and the standard deviation at 1. We're going to go between. So a middle region of 0.95, that would give me a left bound of negative 1.96 and a right bound of 1.96. Now I could test this too. If I wanted to go 0.025, as they found, go above 0.025, that would give us that right-hand side. Take note, that's that 1.96. Or if I typed in negative 0.025, nope, it doesn't like the negative sign. Okay, I get it. Well, it doesn't like negative signs. So, oh, you can't have a negative area. Silly me. We would go below. So negative 1.96. Okay, so that's where this z-score is going to come from. And then we're going to use this because that's going to tell us that we need to go 1.96 sample standard deviations above the mean and 1.96 sample standard deviations below the mean. That's how we calculate this EBM. Okay, and so that's showing that right here. So here was that 1.96 part we calculated using the inverse normal distribution to find our z-score. And then this is the calculation we did last time. This is called our sample standard deviation. You take the standard deviation divided by the square root of the number of terms. All right, so let's put it all together. We have exam scores, normally distributed with an unknown population mean and a population standard deviation of 3 points. So the standard deviation is 3. A random sample of 36 scores is taken and a sample mean is 68. Find the confidence interval estimate for the population mean exam score, the mean score in all exams. So we want to find an interval of scores that tells us 90% of our data is going to fall between the score and the score. And we know the average is 68. So it's going to be somewhere close to 68. So maybe like 65 to 71, and we'd have 90% of our data. If we get numbers like 20 to 25, it's not going to make sense. It has to be close to the average. Okay. So to do this, we take our average. That's really important because that's going to be used on our point estimate here. Remember, the point estimate is the average. So 68. Then we're going to go ahead and calculate this EBM. And to get that, we need to go and think about our confidence level. So we were at 90%. So we need to find the 90% confidence level, find out what that z-score would be. So to do that, we could go ahead and look at our inverse normal distribution curve. I could type in 0.9, 90%. And I go between, and it tells me negative 1.645 and 1.645. So I go left of the mean 1.645 and right of the mean 1.645. So that is this value right here. Then we need to calculate the sample standard deviation. So we use the standard deviation given, that's 3, divided by the square root of the sample size. And they told us on this problem the sample size is 36. So 3 divided by the square root of 36. Well, the square root of 36 is 6. 3 divided by 6, 1/2. So we're going to go ahead and get 1/2 for that value. So down here, they're showing kind of, they're just explaining where this 1.645 came from. We just used the calculator here to get that. So now, here's how you can type it into the, or here they're showing the calculator, but we don't really need to do this on our, we don't need to use the inverse normal on our calculator because we used the other calculator on the computer. So here we go, the z-score, 1.645. Standard deviation is 3. Sample size is 36. Square root of 36 is 6. 3 over 6 is 1/2. 1/2 of this number is 0.8225. So that's our EBM, our error bound mean. So now we take the average, we subtract that EBM. Take the average, we add the EBM, and there's our range of values. So between 67.17 and 68.82, we get 90% of our averages. So if we take this test and do it again, 90% of the time, the class average will fall in that range. Here's how to do it on the graphing calculator if you're curious. Here they interpret it, estimate. We estimate with 90% confidence that the true population average exam score for all stats students is between those two numbers. And believe it or not, there is a little calculator you can type it into, which you should know how to do it all as we did it there. But if you want to check your work, I typed in confidence interval calculator. And you can pick what you know. So we know our sample size was 36, sample mean was that. Deviation is here, and our confidence level is 90%. And there we go. It rounds it a little bit, but 67.2 to 68.8. And there's a little interpretation, and pretty nice. And so notice we can change this. If we want a very high confidence level, that means it's going to have a much wider region because we want almost all the times we run this test to fall in that. So very wide region there. We want to, if we don't want to be super certain, just 80%, it's going to be a very tight region because 20% will fall on the outside of that. So there we go. And that is our first video on this. We'll look at a few different examples next.